For this example for applications of integration, we want to find the volume of a solid obtained by some given curves here about a specific line. This time our approach is going to be, we're still going to use two curves here, but instead of rotating the area about the x-axis, this time we want to do it about the y-axis. There's no particular reason why we have to do it about the x-axis every time, other than the fact that, hey, it may be someone's prerogative here. So the purpose of this particular example is just to make sure that one can understand how to do integration about the y-axis as well as the x-axis. So the previous example I did, if you watched that particular video, I did an example where the rotation was about the x-axis. So this time I want to demonstrate how to do it about the y-axis. So here we see that for these two particular functions that we have, which is x equals y squared and x equals 2y, we see that the independent variable now is the y-axis and the dependent variable is the x. Sorry, I said that wrong. The independent variable is the y and the dependent variable is the x. And so with that being said, we're going to rotate this particular area about the y-axis this time. And so if you see the bottom figure there, I've tried to do my best to demonstrate what that particular figure would look like. And so if you watched my last video, you notice that I used the disk method in order to figure out the areas. And so the idea here is that we want to take a summation of all the areas for this particular solid. Now here, since we have two functions that sort of have a gap in between it, and we're not depending on the x-axis to be a barrier for us or a bound for us, another method that we can use that'll be good is called the washer method. And so what it does is it takes into account of the area that's created by what's called the outer radius, or the function that is greater than, and the area that's created by the inner radius, which is the function that is less than, and it takes the difference of those. And so here we know that for the area of a wafer or a circle, that's going to be A equals pi r squared. But here, if we're looking at it, we have one wafer that's larger stacked on top of another wafer which is smaller. And so what we want to do is get the difference in between the areas of these wafers. And so hence, that's why we have this particular formula for the area. So we have pi times r, which r will be outside radius minus the inside radius, squared. And so writing it another way would just be pi times outside radius squared minus pi times inside radius squared. And so that's the approach that we're going to take here. Now, one last thing before we actually start to do this particular problem. Notice that since we're rotating about the y-axis here, that means we have to integrate about the y-axis. So what that means is when we do our infinite sum, or our integration here, we are going to integrate from 0 to 2, which is from here to there, and not from 0 to 4, since our functions here are written in terms of y and not of x. And so our area here is written in terms of y. So everything is in terms of y. Okay? So here, for our area here, if we wanted to figure out what this is, we see that looking at this according to the as treating our x as being the dependent variable here, we see that the function x equals 2y is producing larger x values for us than the function x equals y squared. So in this case, 2y would be considered the greater function and y squared would be considered the lesser function. And so because of that, our area here will end up looking as follows. So I'm going to come here and do it. So our area here will end up being pi times the outside radius would be 2y, and that would be squared, minus pi times the inside radius would be the y squared part, and then that would be squared. So that's what our particular area formula would be here. And so we're going to take these washers and stack them up from down here all the way up to the top, and we're going to add up the areas of those, and that's what this particular integral means. All right, so with that being said, let's go ahead and attack the problem here. So we know that we're integrating from 0 to 2. We know what our area formula is, so I'm just going to factor out the pi, and we have left here 2y squared is just 4y squared, and y squared would just be y to the 4th. And then that would just be dy. And so from there we'll go ahead and integrate. So we just have pi, and then if we integrate 4 times y squared, that will be 4y cubed over 3 minus y to the 5th over 5, and that will be evaluated from 0 to 2. And so here we know for our second term here, we're going to end up getting zeros. So all we really need to do is evaluate the first term. So our first term here would be 4/3 times 2 to the 3rd power minus 2 to the 5th power divided by 5, and then minus 0, because we plug in 0 for both of these when we do the subtraction part, and we get 0. So cleaning this up, we'll have 2 to the 3rd power is 8. 8 times 4 is 32. So 32 over 3 minus 32 over 5. And once we're done cleaning all that up, we'll see that our answer here is 64/15 times pi, and again this will be in cubic units since we are finding volume. So to repeat, we started off with two functions, and we wanted to take the area that was bounded in between them, rotate it about the y-axis in order to come up with the solid of revolution for that, and we wanted to calculate the volume. Since we were not depending on the x nor the y-axis as one of the bounds to rotate either one of these functions by, or rotate this area by rather, we chose to use the washer method for calculating volume. And basically what that is we use the washer method to say, hey, we're going to take two discs and take the difference in between them, where one has a larger radius and another one has a smaller radius, and use it as our area. And so imagine that we're going to take infinitely thin wafers here, starting from when y is 0 all the way up to when y is 2, and stack them up in this shape here, and then add up all the areas. And if we add up all the areas, then we can figure out what the volume is. And so that's what this particular expression here represents. And so from there, we just plug in our formula here for the area, which is pi times the radius of the outer function minus pi times the radius of the inner function. And we've already discussed y2y is the outer function and y squared is the inner function. We come in, we do the integration, we evaluate it at 2 and at 0, do the difference in between that, and clean it up, and we get 64/15 times pi cubic units as our answer.